Maxima and minima, just take derivative minima. Happiness now just assess the 0, 0, 0, 0. Don't forget you must inspect the endpoints as they are suspect. Find the values of a function, look for highs and lows. Local maxima are on an interval. Local minima are on an interval. Global maxima are on an interval. Global minima are on an interval. Interval, 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 interval.
All right, let's take a look at another example of using the first and second derivative test. So I've given you another polynomial function, y equals x to the fourth minus 4x cubed. And we're going to first apply the first derivative test to see if we can identify intervals of increasing and decreasing for the function y equals x to the fourth minus 4x cubed. So we want to look at where the derivative is equal to 0 or undefined. So let's first take the derivative. That's 4x cubed minus 12x squared. And again, that's a polynomial function. It is going to be defined over its entire domain, so there are no restrictions, so it won't ever be undefined. Let's take a look at where that's equal to 0. And right off the bat, you can see that you can go ahead and factor out a 4x squared. And we have 4x squared times x minus 3 equaling 0, giving us critical values of x equaling 0 and x equaling 3. So those are my two critical values that are going to define my intervals that I need to look at. So we want to look at negative infinity to 0. Sorry, that's a little messy. 0 to 3, and 3 to infinity. So to check to see where we're increasing and decreasing, we're going to pick test values in each of those intervals. So I'll use negative 1, 1, and 4 as the values. And I want to evaluate f prime at those particular values. So you'll see here again, f prime of t, v. That's the derivative evaluated at the test value, not the actual function evaluated there. So when I evaluate at negative 1, you guys can check my math, I get a negative 28. When I evaluate at 1, I get a negative 4. And when I evaluate at 4, I get a positive 64. And again, I really don't care much about what the actual numbers are. I care about their signs, that I am negative, negative, and positive. So what that tells me is that in terms of f of x, I am decreasing, decreasing, and increasing. Do not fall victim to what I would call fool's gold here, that you see that you are decreasing and decreasing in a row. So that does not mean that the interval of decreasing is negative infinity to 3. Remember that the function has actually got a horizontal tangent line at x equals 0. So at 0, it is going to have a slope of 0. It's decreasing everywhere but 0 between negative infinity and 3. So I'm going to write that down here, that my interval of decreasing is going to be negative infinity to 0 union 0 to 3. My interval of increasing is going to be 3 to infinity. Ooh, and I see that I noticed up here that I forgot the other part of the infinity sign on that. So 3 to infinity. So there are my intervals of increasing and decreasing for y. Okay, so taking the first derivative and moving on to the second derivative test to look for concavity of f of x. I'm going to look at the second derivative. So let's find y double prime. And that's going to be 12x squared minus 24x. And again, we want to know, where is that undefined or equal to 0? Clearly not undefined anywhere. Equal to 0 though. 12x squared minus 24x equals 0. I'm going to divide through by 12, just to make it a little easier to deal with the numbers. And that yields an x times x minus 2, or x equaling 0, or x equaling 2. So again, my intervals for my second derivative test are going to look like negative infinity up to 0. Oh, that's the ugliest negative infinity I've ever seen. 0 to 2, and then 2 to infinity. So two critical values for the second derivative, giving me 3 intervals to look at. Test values that I'm going to concern myself with, negative 1, 1, and 3. And those kind of make sense given the intervals. And again, what am I concerned with now? I am looking at f double prime. I'm looking at the second derivative evaluated at each of those test values. So again, you can kind of check my math here. I get 3, -1, and 3. Again, my concern, positive, negative, positive. Positive second derivatives are where f of x is concave up. Negative is concave down. Positive again, concave up. So in terms of intervals of concavity, I am concave up on the interval -infinity to 0, union 2 to infinity. I am concave down on the interval just 0 to 2. In terms of what we talked about a little bit today in class, when we go concave up to concave down, when we see a change in concavity from the positive to the negative for the second derivative, it identifies 0 as a location of inflection point. When I go concave down to concave up, so another change, in this case from negative to positive, it identifies x equaling 2 as a location of an inflection point. So if I wanted to find the inflection points, I would evaluate f of 0 and f of 2 to find the y values, and those would give me the inflection points. I actually have a graph ready for you guys to go. Let me pull that up. Here is the graph of f of x. I'm going to put it right down here in the bottom left-hand corner. You'll see in terms of concavity that the concavity matches with what's here, that it is concave up from -infinity to 0. So that's moving in this direction up to 0. Here's your concave up piece. It's concave down from 0 to 2. So there's a change in concavity from here to here. And then again, concave up for the remainder of the graph. So we definitely see that matching. And if you go back to the information from the previous page in terms of maximums and minimums, you'll realize that we did have the minimum value occurring at x equals 3 because we went decreasing to increasing at x equals 3. And if you really go back and look, I didn't really point it out, but what was really interesting was the function was decreasing on the interval -infinity to 0 and then 0 to 3. If you look, you'll see that the horizontal tangent line occurs at x equals 0, but there is no change from decreasing to increasing. So in fact, it's not a local maximum or minimum. It's a Kim Kardashian point. It is something that is there. It doesn't really tell us anything about being a peak or a valley. It's just a point at which the graph changes from decreasing to doing nothing and then decreasing again. So here's another example of using the first and second derivative tests.